All right, we can move to the second case example, and which brings us in France, in Paris. And this case is still in the drinking water domain, and in this case we work together with Eau de Paris, water utility of Paris, in the renovation of their ozone installation for disinfection. So it's still a disinfection kind of water domain, but in this case with ozone. So it's an ozonation reactor, and they had to retrofit or renovate their ozone reaction. The goal there was really to improve the disinfection by maximizing the contact time of ozone in the water, and at the same time minimize the bromide formation risk. Also there we started with their existing design, where the ozone reactor had two ozone injection chambers, initial first injection chamber, smaller one, and then a bigger one, wider second injection. And then we tested also in this case several design optimization options, and we ended up with this optimized configuration that they are currently it's currently being constructed. And what we did, we divided the ozone dose in 3 chambers. So there are 3 ozone chambers and several contact chambers. So it's a more baffled reactor. In this specific case, this is a more complex model. It's a multi-phase model where we also combined kinetics reaction, so CFD plus our AMOZONE model. So in this slide, you can see the 3D, the concentration of dissolved ozone in the existing design and in the optimized design, as well as the bromide formation. So the concentration of bromide along the reactor. So basically, the main conclusion there was that in the existing design, the ozone dose was not delivered optimally. So we had there was gradients of ozone, so low ozone concentration and very high ozone concentration, especially in this second chamber, very wide chamber where ozone is dosed. And in the optimized design, we could avoid this and provide ozone in a more optimal way, and which gives more uniform concentration of ozone along the reactor, while keeping the same bromide formation at the same dose. And then we could quantify the contact time of ozone along the train, along the reactor, and basically with the optimized design we could improve the contact time by 30% compared to the existing design, which also means that we can save a little bit of ozone dose. In this case, it was up to 50% less dose requirement to get the target contact time. Which means that the bromide formation can also be lowered a lot by using less ozone.